3.5 billion years ago, the sun hanging over the Earth was a different star than the one you know. It was smaller in output, cooler, dimmer, not by some trivial amount, by almost a third. Now take that fainter sun and run it through any climate model we have ever built. The answer comes back the same way, every single time. The Earth should have been frozen, solid, pole to pole, a dead white ball. And yet the rocks from exactly that era are soaked in the opposite story. Liquid water, rivers that cut channels, oceans deep enough to swallow lava, and, pressed into the stone, the chemical fingerprints of life. So one of two things has to be true. Either our physics of how the sun burns is wrong, or something kept a planet that should have frozen warm and wet for over 1 billion years. 50 years on, we still cannot say which. This is the faint young sun paradox. It is not a footnote. It sits, quietly, underneath almost everything we believe about how a world stays alive, including our own. Chapter 1. The Dimmer Star. To understand the paradox, you have to start with the part that is not in doubt at all. The sun really was fainter. And we know that not from guesswork, but from the most thoroughly tested physics we own. A star is a permanent argument between two enormous forces. Gravity is forever trying to crush it inward. The heat of nuclear fusion is forever pushing back out. A stable star is simply a draw between the two. Astronomers have tested this picture against thousands of stars at every stage of life, from newborn to dying. The model holds. We understand how stars burn about as well as we understand anything in the sky. Deep in the core, under crushing pressure, hydrogen nuclei slam together and fuse into helium. That fusion is the outward push. It is the engine, and it has been running for 4.5 billion years. Here is the subtle part. Helium is heavier and more compact than the hydrogen it came from. So as the core slowly fills with helium ash, the center of the sun very gradually shrinks and grows denser. A denser core has to burn hotter just to hold itself up against gravity. Hotter means brighter. So across its whole life, a star like the sun does not hold steady. It slowly, relentlessly brightens. Wind that process backwards. The young sun had almost no helium ash yet. Its core was less dense, and it ran cooler. The standard solar model puts its output at roughly 70% of what reaches us today. And this is the crucial point. That 70% is not a convenient assumption pulled in to make a story work. It drops straight out of the same equations that nail the sun's brightness today, to the decimal. If you reject the faint early sun, you have to throw out the physics that predicts the sun you can see right now. Almost no astronomer is willing to do that. The dimness is as solid as science gets, which means the mystery was never really the sun. The sun behaved exactly as the equations say it should. The mystery is the small wet planet underneath it that flatly refused to freeze. Chapter 2. The Earth that refused to freeze. So let's do the experiment on paper. Take today's Earth and dim the sun by 30%. The planet's average temperature does not dip a little. It crashes far below the freezing point of water, and cold, it turns out, feeds on itself. Ice and snow are white, and white reflects sunlight straight back into space before it can warm anything. The more a planet freezes, the more light it throws away. Throwing away light makes it colder, which makes more ice, which throws away more light. Scientists call this the ice albedo feedback, and past a certain tipping point, it runs away completely. The end state is a snowball Earth, the entire globe sheathed in ice, sea to sea. And the cruel part is that a snowball is stable. Once you are in one, the whiteness keeps you there. The models say the young Earth should have been locked in one, for good. Except the planet never got the message. The rock record from the Archean Eon, the long stretch between 4 and 2.5 billion years ago, tells a story that should not be possible. There are pillow lavas, the rounded, bulbous shapes that molten rock only makes when it erupts directly into water. Their very presence means there were oceans for the lava to erupt into. There are fine layered sediments that can only settle gently onto the floor of a standing body of water. There are riverbeds with rounded pebbles, worn smooth by flowing liquid. And there are stromatolites, domes and columns built layer by colonies of living microbes, in shallow, sunlit liquid water. Some are 3.5 billion years old. Put it together and the verdict is overwhelming. The early Earth was not a frozen ball. It was warm, it was wet, and it was already, unmistakably, alive. In 1972, Carl Sagan and a colleague, George Mullen, laid the contradiction out in a single paper. A faint sun on one side, a warm, living Earth on the other, both rock solid, both impossible together. They could have buried it as a curiosity. Instead, they named it, and handed the next 50 years of scientists a problem that, even now, nobody has been able to fully put down. Chapter 3. The Greenhouse Rescue. The most natural escape from the paradox is the air. If the early atmosphere trapped far more heat than ours does today, then even a feeble sun could keep the oceans liquid. The sun is weak, so make the blanket thicker. The first and most obvious suspect is carbon dioxide. It is a powerful greenhouse gas. Pump enough of it into the young sky, and on paper the extra warming neatly cancels the missing sunlight. Better still, the Earth has a built-in thermostat for carbon dioxide. When the planet is warm, rain weathers rock faster, which pulls CO2 out of the air. When it is cold, weathering slows, and CO2 builds back up. A slow, self-correcting dial. So maybe the dial simply sat much higher back then. A young Earth with a thick carbon dioxide sky would run warm enough, faint sun and all. For a while, that looked like the whole answer. Then a second suspect arrived: methane. The early oceans swarmed with microbes that breathed it out as waste. And methane, molecule for molecule, is a far stronger greenhouse gas than carbon dioxide. Enough of it, and the sky itself changes color. A methane-rich atmosphere forms a thick orange haze, strikingly like the one that wraps around Saturn's moon Titan to this day. Carbon dioxide, methane, a self-correcting thermostat, a microbial haze. It felt, for a couple of decades, like the paradox was basically solved. Just turn up the greenhouse gases until the numbers fit, and then the rocks pushed back. Because the same stones that prove there was liquid water also quietly record what the air was made of, and they refuse to cooperate. Ancient soils, and minerals like siderite that only form under particular conditions, place a hard ceiling on how much carbon dioxide the early air could have actually held. And that ceiling is often far too low to do the warming job. The methane story has its own wound. Around 2.5 billion years ago, oxygen flooded the atmosphere in the Great Oxidation Event. And oxygen destroys methane. The cozy methane blanket should have collapsed right when the Earth still needed it. So, every clean version of the greenhouse rescue runs into a stone that says no. Propose the precise mix of gases that would keep early Earth warm, and somewhere a rock turns up insisting there simply wasn't that much. Chapter 4. The Open Verdict. So the search widened, well beyond the air. And the next idea is almost embarrassingly simple. Maybe the early Earth was just darker. A darker planet reflects less and absorbs more. And the young Earth had barely any continents, almost no ice, and far less of the bright land that bounces light away. A darker world soaks up more of what little sunlight there is. Then there are the clouds. Fewer bright, low clouds would also darken the planet and warm it. But clouds are the single hardest thing in all of climate science to model. They can warm or cool depending on type, and nobody can reconstruct the skies of 3 billion years ago. There is even a wilder possibility out at the fringe. What if the young sun was slightly heavier than the standard model assumes, and therefore brighter, slowly shedding that extra mass on the solar wind over billions of years? A more massive young sun would simply close the gap by being brighter from the start. The measurements needed to confirm it are brutally hard, and most astronomers doubt it, but it has never been completely ruled out. The honest, most likely answer is the least satisfying one. A blend. A little extra carbon dioxide. A little less ice. Some methane before the oxygen came. A darker surface. Each piece too weak alone. The sum, just barely, enough. But just barely enough, holding steady across more than 1 billion years, through volcanoes and ice and the rise of oxygen, is a deeply uncomfortable kind of answer. It looks less like a law and more like a tightrope. And here's the part that should genuinely unsettle you. The climate models that struggle to keep early Earth warm are not some separate, broken tool. They are close cousins of the models we use to forecast our own climate. They are also the models behind every confident statement about which distant exoplanets sit in the habitable zone, the comfortable band where liquid water, and maybe life, could exist. If we cannot fully explain how our own planet stayed warm and wet through its first billion years, then every neat circle we draw around a habitable zone rests on a paradox we have not actually closed. For 4 billion years, something held a freezing world warm, long enough for oceans to settle, long enough for life to take hold and never let go, long enough, eventually, for you to be standing here asking why. We have suspects: carbon dioxide, methane, a darker, cloudless sky, maybe even a heavier sun. What we still do not have, after half a century of looking, is a verdict. The faint young sun is a quiet reminder that the most basic question of all, why is it warm enough, right here, to be alive, does not yet have a finished answer. If you want more open mysteries like this one, the channel is